Saxon Algebra 1, Lesson 82, we're going to talk about functions. You guys, the math in this is really, really easy. There's nothing tricky about that. It's just kind of a vocabulary / concepts lesson. So it's not hard, but it's a little weird. We're going to toss around some words that probably are not your favorite math words. But just kind of stay loose, shake it off if you start to feel crazy, and just recognize that this will make sense after you've heard it a few times. We'll be talking about it a lot. But there's no difficulty in the math. That's not the hard part at all. All right, we're going to warm up with some easy lobs. 82.1. If f of x equals x squared plus x minus 10, okay, I'll give you a second to copy that down. That's an exponent. It's kind of messy. Plus x minus 10. Okay, good. All right, what this notation is saying to us is, hey, here's an expression, an algebraic expression that we could plug a lot of different numbers into. Right now, we're just writing it with variables. We're using x, and we're saying the name of this function is f. All right, with functions, we always start out with f, but you can go on through the tradition is start with f and then go on g, h. We skip over I, j, k, l. You go all the way down. You can go all the way through the whole alphabet, and if you're still working on the same topic, and you come back around, you can do A, B, C. You can even then get into double Fs, right? So that's what's cool, again, about this functional notation thing, is that it's a way to name your functions so you can talk about different ones at the same time. Now, what does this f of 5 thing mean? That just means plug 5 in for x. So when we wanted to find the f of 5, right, this is the f of x. There's the generic thing. When we want to calculate the f of 5, that means plug 5 in for x. So that's what we do. It's super easy. It's like those evaluation problems that we've been doing for a long time. I was just doing some with the Algebra 1/2ers. You just plug it in. It's not hard. Again, the math is super easy. Just don't let it psych you out. So then we can keep saying the f of 5 is 25 plus 5 minus 10. The f of 5 equals 20. Whoa, accent kicked in. Fake accent. All right. Does that make sense? That's all this notation means is there's the generic form. Plug in 5 and see what you get. Okay, let's do another one. (82.2). Oh, this one's the h of x. We skipped over g, but that's okay. Okay. Now, this one, okay, that looks fine. Doesn't look all that different than that one. Find the f of 5. That was easy. We just took the 5 and plugged it in wherever there was an x. This one seems really random because instead of having a number, we have different letters to plug in. So wherever there's an x, we put in an a squared. All right, now this one it's helpful. I didn't use buckets completely on this one. I'm going to use buckets on this. The h of a squared equals, okay, so we'll put, there's one set of buckets where there's an x, and there's another, and then there's a plus 1. So I put my a squareds into the buckets where there used to be an x, right? This square is there. There's the plain x, and the a squared goes into the bucket where the x belongs. Weird, right? It's a little bit messy. So then this becomes the h of a squared equals, now how do we simplify this? Oh, we have the power rule, right? When you've got a base raised to a power, you multiply them. And your base raised to a power and you're raising it again, is what I'm trying to say. That's our power rule, which you guys memorized beautifully for me. So proud of you. So this becomes a to the fourth plus a squared plus 1. And that is our final answer. That's the h of a squared. Yay, that's also correct. Okay, we're going to do one more of these, and then we're going to start being more headbendy. If the f of x equals x squared plus 1, find the f of x plus 2. Oh, Lord have mercy. It's a binomial. It's a binomial. So we're plugging in this everywhere there's an x. All right. So I'm going to make bigger buckets this time for that. So then we put x plus 2 into the x bucket. All right, fine. But now we have to multiply the binomial times the binomial. That's the kids dancing in the studio, right? We can't just say x squared plus 4. That's cheating. We can't do that. What we have to do is we have to multiply out binomial times binomial. This, again, is the scenario of the kids. I imagine it like an old-fashioned dance studio. So like on Saturday mornings, the kids in the town, like back in the 1930s or something, where kids in the town, some small town had to be taught they had to take dancing lessons, so they would be like cultured teenagers. And so some woman taught lessons in the second floor up above some store, and there were big wooden floors and giant windows, and the sunshine poured in, and there were metal chairs lining up on the wall along the two walls. Now these two are switched together. I imagine it being a big room like this. I have to let you into my brain. And here's the chairs where the boys sit. And here's the chairs where the girls sit. I always imagine the windows are here. And that's where the light streams in. And then on this side, on this wall, is a mirror. There's the little shiny spots on the mirror, so you can tell it's a mirror. Okay? Now, so these are the boys and these are the girls in our number. Now, one at a time, the teacher assigns partners of who needs to dance with who. And she has just one set of kids dancing at a time so she can critique them, right? So these are the boys and these are the girls. My metaphors are very complicated, aren't they? This girl starts first. She dances with that boy. When they dance, we multiply, okay? And I'm going to write my answer out here. I'll move my whole problem because I've made a mess, haven't I? Okay, she dances with him. That's x squared. Then, when that's done, the teacher has her dance with the other boy. That's 2x. Beautiful. She's done. There's only 2 boys in class this day. Now it's the other girl's turn. She dances with the first boy, 2x, and then the second boy, 4. X squared plus 4x plus 4 is what we get when we square that binomial. So I'm going to sort of put the dancing studio separately. The f of x plus 2 equals, now all of this goes in here, x squared plus 4x plus 4 plus 1 more, right? And so our final answer is that the f of x plus 2 equals x squared plus 4x plus 5. Add those like terms. Guess what? That's the right answer. Yay! Okay, so plain number, letter with an exponent, binomial. We can plug anything in. Sometimes it creates drama when we go to simplify it. But basically, it's all working just fine. All right, that's how we evaluate functions. Now, let me tell you something. There are 2 fancy words. We've dabbled in them briefly. The number that we plug in, and I'm going to say value because it can be a letter or a number. Okay, that's what was right here. Like we plugged in 5 and we plugged in a squared and we plugged in x plus 2. That's called the domain. What we plugged in. Okay, the answers answers that we get, which are here and here. Our paper's getting super messy, huh? I hope you're copying everything that I am. And then way over here. Those are called the range. It's that simple, you guys. The domain is what we plug in. The range is what we get out. Okay? And now we're gonna take these ideas and we're gonna apply them to graphs, and I'll show you that in a minute, but I just want you to put this in your notes. Domain is associated with X, and range is associated with Y. Okay, which makes sense because we usually use X here, right? So we plugged that in for X. All right, so copy this, keep it in your head, and we're gonna go on and we're gonna use that information. I will let you copy it. Okay, and that's what a function is. A function is a mapping or a connection between a domain and a range. And that's what we did here. We took an item from the domain and we found its range. Domain, range, domain, range. So these are not new ideas, you guys. They're just fancy words for old ideas that seem moderately frightening because domain and range, I mean, those are regular words, but they just sound creepy. All right, now what we're going to do is something that is going to seem so weird at first. It's that we're going to think it's hard, but it's not. If f of x equals 2x, find the domain and range of this function f. All right, now this is going to make a lot more sense when we have an exception to this, but if we have a function like this, are there any limits on the numbers that we could plug in there? No, we could put in positive numbers for x. We could put in negative numbers for x. We could get fractions, decimals, right? We could do radicals, right? That wouldn't hurt anything. We could put a radical in there for x. We could use anything we want. So what we say is that the domain of x equals the set of all real numbers, which means go ahead, throw anything in there. It's fine. And if we do that, we'll be able to calculate another value, right? And there's no limits on what that can be. So when we talk about our range, we write the range of f, which seems weird. It seems like we should put y, but when we're talking about functions, we don't really talk about y's. The y we now call the f of. Okay, that's kind of weird, but it just, we can live with it, right? The range of f, we can get any real numbers out of this too. This is so easy, it seems hard. You're sitting there going, what? How did she even do that? Let me try another one. Over the next couple examples, this will become more clear to you. 82.5. This time, our f of x equals 3. Now that's a weird looking function because it says no matter what we plug in for x, letter, number, binomial, exponent, anything, the answer will always be 3. What? That seems weird. But we could put anything in we wanted, right? Again, radicals, percents, decimals, fractions. So the domain of x equals the set of all real numbers. We will do one where this is not the domain. But here's the fun part on this one. The range of f equals 3. Right? No matter what we put in, oh, I'm sorry, I'm putting it the wrong one. No matter what we plug in here, the answer will always be 3. So that means we can limit our range. It's just 3. There'll never be anything else. So this one's a little bit different. By the way, these are the answers, and these are correct. All right. I'm going to skip around a little bit because I want to do one now that will help you see the exceptions better. This is 82.8, and this is the last one. Find the domain of the function g of x equals 1 over x. Now, this one is much easier to understand because we see that we're going to be putting our variables in the denominator, And there are some rules about denominators, right, that are problems. And the biggest one is no zero. We are not allowed to put 0 in the denominator of a number because it will blow up the kingdom, right, and destroy the universe. So we can't allow that to happen. So in this one, John just wants us to write the domain. Here we write the domain of G equals, and now we can get into some fancier notation. X is an element of the real numbers such that X is not equal to 0. That's our answer. Because we can't just say, oh yeah, instead of all real numbers like we did here. This is fine. This is a fancier type of notation. They mean the same thing, but I added this line which says X, we cannot let X equal 0 because we can't blow up the universe. That one's more interesting, isn't it? This one's boring. I don't like it. And it just seems confusing. Let's do another one. Find the domain of this function. F of x equals square root of 5 minus x. Now, here's something we know, but you might not know you know it, so let me remind you. In square roots, we can take the square root of anything as long as it's a positive number or 0. It's okay to have 0 in here. Square root of 0 is 0. But we can't have a negative sign in a square root. That doesn't work at all. In fact, that's where we get into something called imaginary numbers that we'll deal with later. But that's not allowed. We can have no negative numbers. In an even numbered radical. Okay? There's no number there, so we know that it's an invisible 2. It can't be negative. We'll talk more about why that is as we go on. I don't want to belabor that right now. I just want to tell you this is a rule. Remember it. This can never be allowed to be negative. So that means that the domain of F, let's use this pattern again, equals X is an element of the real numbers such that X is greater than or equal to 5. Oh, I'm sorry, less than. Sorry. Right? This 5 minus X can never be, let me just write it like this. 5 minus X has to be greater than or equal to 0. Does that make sense? This is why I'm getting confused. 5 minus X cannot be less than 0. It's got to be greater than or equal to 0. So we add X to kind of solve this little thing. 5 has to be greater than or equal to X. Then I took this and I wrote it in the opposite order, and that's why I got confused, because I was thinking of it this way. But X must be less than or equal to 5. That'll keep this a positive number, right? For example, if X were 6, that would give us a problem, wouldn't it? Because that would equal the square root of -1. So X can't be any bigger than 5. If it's 5, we're fine, right? Because the square root of 5 minus 5 would be 0. So we're good with that. So here's another example of a function that's a little bit more interesting, that bumps up against a rule, just like this one bumped up against a rule. This first one and the second one, to a point, were really confusing because it didn't bump up against any rule. It's just like, sure, go ahead, put in whatever you want. These two are more interesting because they have rules. You can't have 0 in a denominator, and a square root of a even numbered root, a square root, or it could be a 4th root or a 6th root. As long as this is an even number, this number can never be less than 0. No negative numbers in an even numbered radical. Okay, so these two rules you have to lock into your brain so that when you're doing these problems and you see a function like this, your brain will go, oh, this is drama. I need to be careful and limit the numbers that go in there. Okay, one more. And this one's a little bit different, and it always throws students off, but it's super easy if you can just wrap your brain around it. I'm going to replicate the picture. Here is a graph. And then, oh, this is a circle. Sorry. Okay, and then we can fill in the numbers on these if we so desire. 1, 2, 3, 4, minus 1, minus 2. Okay, I'm going to stop right there. Now, I'll give you a second to finish sketching. John asks us, he tells us this is the graph of function f. Okay, it's a function named f. And he wants us to find the domain and the range. Now, do you remember what I told you on that other page? Okay, I told you that domain is associated with x and range is associated with y. Right? The domain is what we put in, the range is what we get out. That kind of corresponds to the way we usually pick our x's and calculate our y's. It kind of fits together. Don't worry if that doesn't make sense to you. Just know that x goes with domain and range goes with y. Okay, so if we want to find the domain, what we want to do is we want to look at the x-axis and we want to look at the beginning and end of this function. This is a picture of a function. Okay, it's not an infinite function, it's finite. So we can see that our function includes all the real numbers, right? Because it fills in all the little blanks in between, right? It's not just the integers. It's all the little fractions and decimals in between, so it's the real numbers such that, now the lowest number is minus 2, but there's a circle there. So that means we don't include minus 2 in our answer, but it just goes up to minus 2. And then these are all the values of x, and then the highest value is 3, right? That comes down right here. That comes down right there. So x fluctuates between 3 and negative 2, 3 inclusive, negative 2 not inclusive. That's why I put just a greater than here, but I put the equal sign under that one. So I use this picture and I just follow these lines down, and then those are the two values that x ranges between. I shouldn't say range because that sounds like this. X falls between these two extreme points. All right? That's all you have to do. It's so easy. And a lot of students freak out over these and feel like they're really hard, but they're not. Now let me just do range in another color. The hardest part of range is we have to flip our brains, and now we're looking at the y-axis, right? Because range is about y. And so we do the very same thing. What's the highest point that this function hits on the y-axis? Right there, right? This is lower. This is at 3, right? Because we're comparing it to this scale now. Just changing your perspective is the hardest part. And then it goes all the way down here to 0. So we can say that y is an element of the real numbers such that, let's see, it's from 0, and it does include 0. So we can put the equal sign there. There's no circle there. I put the dot. But if you look at the picture in the book, it's solid there. There's no circle. And then it goes all the way up to 4, and that's a solid as well. So I can put equals on both of those. Does that make sense? They're not hard. All you have to do is look at the picture and read the highest and lowest values. It's super easy, but it's a little mind-bendy because you have to like reorient yourself from one axis to the other. And you have to remember that domain is always associated with X. And look, there's where we put an X. And Y is associated, or range is associated with Y, and there we put the Y. Yay! Lesson 82 is done. This one was a little bit conceptually challenging. We'll be talking more about these things as we go. They'll get more familiar. If you feel like you can still say the ABCs and you know your address, then I think you're doing really well. Okay, thank you, goodbye.